Hello everyone, welcome to our channel Data Breaks I. Today we are going to discuss the difference between low and high dimensional data. Once the difference will be clear, it might help you to analyze the raw data before going to ML or AI techniques. So here you go. The terms low dimensional and high dimensional refer to the number of features or dimensions in a dataset. Here's a brief explanation of the differences between low dimensional and high dimensional data. Low dimensional data. In low-dimensional data, there are relatively few features or variables. Visualization is often straightforward in low-dimensional spaces, as it is easier to represent data in 2 or 3 dimensions. Analyzing and understanding relationships between variables is usually simpler in low-dimensional spaces. Examples of low-dimensional data include simple spreadsheets or datasets with a small number of columns. High-dimensional data. High-dimensional data refers to datasets with a large number of features or variables. Visualizing high-dimensional data directly can be challenging, as humans can easily visualize only up to 3 dimensions. Analyzing and interpreting relationships between variables become more complex as the number of dimensions increases. High-dimensional datasets are common in fields like genomics, image processing, natural language processing, and machine learning, where data often involves thousands or even millions of features. Now we are going to explain low and high dimensional data with example, visualizations, analytical simplicity, and computational efficiency. Low dimensional data. 1. Example. Imagine a dataset with information about houses, including features like square footage, number of bedrooms, and price. This dataset might have only 3 dimensions: square footage, number of bedrooms, and price. 2. Visualization. In a low-dimensional space, you can easily visualize the data using scatterplots or 3D plots. Each data point is represented by a point in a 2D or 3D space. 3. Analytical simplicity. Analyzing relationships in low-dimensional data is generally straightforward. For instance, you can visually inspect how changes in square footage or the number of bedrooms correlate with changes in price. 4. Computational efficiency. Algorithms applied to low-dimensional data tend to be computationally efficient, and it's easier to apply traditional statistical techniques for analysis. High-dimensional data. 1. Example. Consider a dataset with customer information for an e-commerce website, including features like purchase history, time spent on the site, device type, location, and more. This dataset might have dozens or hundreds of dimensions. 2. Visualization challenges. Visualizing data in high-dimensional space is challenging due to limitations in human perception. While we live in a 3-dimensional world, representing data beyond 3 dimensions in a way that is easy to understand becomes practically impossible. 3. Curse of dimensionality. The curse of dimensionality refers to the increased sparsity and computational complexity that comes with a higher number of dimensions. As the number of features grows, the amount of data needed to generalize accurately also increases exponentially. 4. Dimensionality reduction. Techniques like principal component analysis, PCA, or T-distributed stochastic neighbor embedding, TSNE, are often employed to reduce the dimensionality of the data. These methods aim to capture the most important information in the data while discarding less informative dimensions. 5. Overfitting. High-dimensional data poses challenges for machine learning models. With many features, models can become overly complex, capturing noise in the data rather than true patterns. This is known as overfitting. 6. Specialized algorithms. Algorithms designed for high-dimensional data, such as regularization techniques in machine learning, help mitigate the risk of overfitting and improve model performance. In summary, while low-dimensional data is more manageable in terms of visualization and analysis, high-dimensional data presents challenges that require specialized techniques to extract meaningful information and build effective models. The choice of analysis methods depends on the dimensionality of the data and the goals of the analysis or modeling task.